In this lesson, I'll discuss various sources of nutrient pollution and show some data on relationships between intensive animal agriculture and these problems. There are a variety of sources of nutrient pollution of air and water resources. The major ones are presented here. Urban stormwater. This flows to wastewater treatment plants, but in cases of storms, usually there's overflow that bypasses the treatment and is discharged directly. Also, lawns and golf courses if we over-fertilize. And agriculture, all forms, including animal agriculture and cropland. Also, septic systems that handle the waste from a significant proportion of houses in the U.S. And atmospheric deposition. Remember, we talked in the last lesson about ammonia. These are all sources of nutrient pollution of air and water resources. Which one is the dominant source really depends on where you're located. I'll tell you a story that may or may not resonate with you. So, like many of you, maybe I have a younger brother, and when I was growing up, my younger brother was kind of a pig. He's turned out to be a very responsible human being, but as a child, he was a slob, and his room was always a mess. And so when my dad would say, "Catherine, pick up your room," I'd always say, "But Philip's room is way messier than mine." My dad would say, "Clean up your room, and then we'll talk about your brother's room." That's kind of how I feel about the nutrient pollution question. It's easy to get up in arms and say, well, in this area, it's all those golf courses, and in that area, it's all those septic systems. But in animal agriculture, we do have a nutrient surplus challenge, and let's focus on solving that, because that's what we can control, and there are solutions to be had. As we discussed in the previous lesson, there are many areas of the United States, and in fact around the world, where intensive animal agriculture industries have developed. These farms import and concentrate nutrients. Many generate manure nutrients in excess of what local crops need. And unfortunately, these excess nutrients do have negative environmental impacts. The U.S. Geological Survey collects water quality data from sites across the U.S. and uses computer models based on research data to predict concentrations of various pollutants. This map is of nitrate concentration in groundwater, with orange and red indicating areas with elevated nitrate concentrations. Pay attention to the areas in red. Compare those areas of elevated groundwater nitrate to this map with areas of intensive animal agriculture. Now, I will say that the group that created this map has an anti-large farm bias, but the data the map is based on is sound. Again, there's an association between intensive animal agriculture and elevated nitrate in groundwater. This map is more complex, but it's worth spending some time on because it indicates some progress being made in some areas of the country, although not others. This is data from groundwater sampling over time from 1998 to 2012. The map indicates changes in groundwater nitrate concentrations over that 15-year period of time. The orange arrows indicate places where nitrate concentration increased in that 15-year period. Green is where nitrate concentrations decreased. Big arrows mean big changes. Little arrows mean little changes. The black dots are sampling sites where no change was observed. The good news is that there are many areas of no change and a few areas of reduction. So at least groundwater nitrate in many areas appears to be plateauing. The good news is that it looks like soil nitrate levels across the U.S. are plateauing or even dropping. This is the same map as I showed on the previous slide, but 2012, 2013, and 2014 data. You can see many more sites where there's no change in groundwater nitrate, and really only the one site out in California that's showing an increase in groundwater nitrate. So we've at least stabilized the trend. I've got a few more slides with maps on them to show you, and then we'll shift gears and talk about whole farm nutrient balance, but let's stay for now on the subject of the sources of nutrient pollution. The previous slides focused on groundwater. This map and the next one focus on nutrient export from farms to surface water. Now, this data is dated. It's through 1998, put together again by the U.S. Geological Survey. It's the result of intensive water quality sampling, ag census data, and computer modeling. The primary point I want to make is that relative contributions of different sources varies by location. In some areas, wastewater treatment plants or commercial fertilizer are the dominant inputs. In others, it is animal agriculture. So on this map, the areas in blue are where something other than animal agriculture are the primary contributors to nitrogen loading to surface water. In contrast, that brown and the red are areas where animal agriculture is the dominant source of nitrogen export. This data is useful for identifying where to focus efforts for improvement. At the time of this USGS survey, animal ag was the dominant source, more than 50%, in parts of the panhandle of Texas, also in northwest Arkansas and northeast Oklahoma, home to a significant broiler industry. Notice that the Eastern Shore and Shenandoah Valley are also flagged. The other point I want to make with these USGS maps of sources of nutrient pollution to surface water is that animal agriculture is much more of a concern for phosphorus loading than for nitrogen loading. This map, as in the previous, it indicates in blue areas where animal agriculture is not a big source of the problem, that there are other sources that are contributing primarily to phosphorus loading to surface waters, but the areas of brown and red are where animal agriculture is the dominant source of phosphorus export. So animal ag is much more of a concern in terms of phosphorus than in terms of nitrogen. So why is this? So why do areas of intensive animal agriculture seem to be so much more of a phosphorus issue than a nitrogen risk? Here's the basic problem, and it's a really important concept. Manure nutrients are in imbalance relative to crop needs. Crops don't need very much phosphorus, and there's too much of it in manure relative to the available nitrogen in that manure. Stay with me. Here's an example. I've chosen corn silage as an example crop. On good land in this example, this corn silage might require 185 pounds of nitrogen per acre to supply the needs of the crop. But that same corn silage only will require about 80 pounds of phosphorus per acre. Now, if we use commercial fertilizer, we can match these needs exactly, leaving minimal opportunity for nutrient loss. So this is what an example corn silage would require. But on livestock farms, we have manure as a resource. We use manure to fertilize crops, and it's an excellent use of a resource. However, we have this imbalance. If we apply dairy manure to meet the nitrogen needs of that corn silage crop, we will be putting down more phosphorus than the crop needs or can take up. In fact, a lot more. The relative ratio of nitrogen and phosphorus in manure varies, and that'll be the subject of future lessons. But almost always, if we apply to meet the nitrogen needs of the crop, we are over-applying phosphorus. And it can be worse with other manures. Poultry litter, for instance, the combination of manure and bedding collected from poultry houses is very nutrient dense. It's great fertilizer. Except that, it's got way too much phosphorus. To be clear, what I'm showing in this graph represents applying a quantity of manure to meet the nitrogen needs of that example corn silage crop. So, in this example, I'm applying dairy manure to supply 185 pounds of nitrogen. Or I'm applying poultry litter to supply 185 pounds of nitrogen. That's the green. What I want you to see is that the phosphorus that comes along with that nitrogen is much more than what the crop needs. Over time, this leads to accumulation of phosphorus in soil, and at some point, varying by soil and by management, that surplus phosphorus can run off, contaminating surface water. I'm going to walk through this another way. If we apply manure to meet the nitrogen needs of the crop, understand that nitrogen and phosphorus are in imbalance in livestock manure relative to crop needs. So if we apply to meet the nitrogen needs of the crop, and that is called nitrogen-based application, we will be applying excess phosphorus. The phosphorus can accumulate and may run off even without erosion. An alternative, instead of applying to meet the nitrogen needs of the crop, we can scale back our manure application and just meet the phosphorus needs of the crop. That's called phosphorus-based manure application. Let me show you what that would look like. So in this figure, I've flipped it. We're applying manure to meet the phosphorus need of the corn silage. The blue is the phosphorus, and I'm applying dairy manure or poultry litter to supply 80 pounds of phosphorus per acre, which is what the corn silage needs. The green is the nitrogen need of the corn silage, or the nitrogen supplied by the manures, and you can see the problem. When I put down dairy manure to match the corn's phosphorus requirement, I am way short on nitrogen. It's worse with poultry litter. If I put down the amount of poultry litter to match the corn's phosphorus requirement, I am way short on nitrogen. So I can't grow corn without providing nitrogen. That means buying commercial nitrogen fertilizer to make up the gap. And that's an expense that farmers really don't need. So to reiterate, phosphorus-based manure management is when we limit the manure application to the phosphorus needs of the crop. We will fall short of the nitrogen needs of the crop, meaning we've got to purchase nitrogen fertilizer. And in fact, if your soil tests show a high or a very high level of soil phosphorus, the crop needs can be met by the soil phosphorus without needing any manure application. But the crop's still going to need nitrogen. And that's exactly the situation we're in areas of intensive animal agriculture. You remember we talked about how important animal agriculture is in the Shenandoah Valley in Virginia. Most of the state's poultry and dairy industry is concentrated there. Rockingham County in Virginia is number one in the state for both industries, tremendously economically important. But the impact of this intensive animal agriculture on soil phosphorus is clear. The state soil testing database indicates that nearly 90% of the soils in that county test high or very high for phosphorus. Now, the soil test phosphorus at which runoff occurs varies by soil type and various land features. We'll talk about that more later in the course, but clearly these soils need no additional phosphorus, but we got an awful lot of manure to utilize. And I'll stop this lesson here with just a summary and a reminder of the key concepts.